Thank you very much. I've had most of my super hot material removed from me because of non-disclosure agreements with Mazama, who are currently drilling on a volcano in the US. The reason that I wanted to talk about what we're doing there is that actually the conditions there are almost identical to what we would expect to see within the hotter provinces of Taiwan. We also are putting in place an EGS system that's very similar to what we were proposing would be the best way forward for Taiwan and the larger power developments in Taiwan. Please remember that you already have hydrothermal reservoir dependent options, and they should be explored first because they are the lower technology route. However, with potential to use electrical reservoir stimulation, some of the EGS projects could come online a lot quicker than maybe with conventional hydraulic fracking. One of the other problems we have, and sorry to be me again, one of the other problems we have in very hot geothermal wells is how do we manage the compressive loads in the casing strings that are created when we heat that steel up. As we heat the wells up under production, that casing string wants to expand, and if we allow it to expand over its whole length, it will buckle, the casing couplings will start to collapse. We'll have all sorts of integrity issues. So this project came out of a completely coincidental sequence of events. I was asked by OSI Renewables to put a training course together for them and go in and train their team on what is geothermal, where are the opportunities in geothermal for OSI Renewables. What they wanted to do was kind of put a portfolio of technologies together from their oil and gas technologies that would be branded into geothermal. And while I was teaching this course, there was a beautifully made model sitting on the windowsill. And at break time, I went and I started playing with this. And I said, what is this? And they said, well, it's actually the tendon tensioner from a tension leg platform. So as these steel cables come up from the seabed, they go into these tendon tensioners, and we pre-tension the platform so it sits level. But obviously, we need to regularly rechange that tension and adjust the tension so they can't just be bolted together. And I looked at it and I scratched my head a little bit and I thought, I think there's another use for this technology. I think if we make a wellhead with the same system, that will allow us not to have to cement the entire annulus all the way back to surface. That has huge potential benefits for our geothermal wells, because if we can maintain the annulus like we do in an oil and gas well, it has huge possible savings in cost, and it potentially increases our safety. If we can monitor the annulus and put real-time monitoring in the annulus, we can have 24 hours a day surveillance and smart alarms that tell us if we've got a well integrity problem a long time before we risk compromising shallow aquifers. One of the problems that we've seen in geothermal development, one of the problems we've seen in geothermal developments worldwide is that the older developments where the understanding of corrosion, the understanding of cement integrity hasn't been there, we've got contamination of drinking water aquifers. If we look at Paris, for example, I can't remember the exact numbers, but of the 60 geothermal heat wells there, something like 20 of them are shut down because of corrosion problems, and some of them have actually catastrophically contaminated drinking water aquifers. So we don't want that, But if we're cementing all the way to surface and we have a leak path in the cement that develops over many years, we won't know anything about that till somebody says the drinking water tastes a bit salty. And that's a best case scenario. If we maintain the annulus all the way to surface and we've got instrumentation on it, the minute that we get an integrity problem, the alarms will go off and we can address that problem straight away. And in some regulatory environments, if we have that capability for 24 hours a day surveillance, it might mean that we don't have to shut down all of our equipment and our well periodically to do a full inspection, a use-it inspection, an ultrasonic inspection, a multi-finger caliper inspection, things like that. So the idea behind this technology is that we cement conventional. How much retarder do you put in for the cement coming close to surface versus the cement down in the hot part of the well? If we don't put enough retarder in and we're pumping and cementing a hot well conventionally, and conventionally means the cement goes down inside the casing and comes up the annulus, what will happen if we don't have enough retarder in, that the cement will start to set up as we go round the hot part of the well. If we put too much retarder in to let us get past that hot part of the well, the cement that ends up in the cold part of the well will never set. So we're potentially compromising our cement job trying to get a full annulus filled. So we can cut our cementing costs, we can make a more robust cement job. And the risks of a poor cement job are voids and channeling that we're unaware of that allows subsurface flows. But if we've got a channel or a void against an impermeable rock, when we heat that well up, that fluid will expand and collapse the casing. So we potentially have a higher potential for failure within that environment. One of the traditional ways of managing casing compression is by increasing the wall thickness of the casing. Your casing string compressive performance is a function of your wall thickness, and that's the primary way we deal with buckling resistance in most drilling and well construction. The problem with that in geothermal is that you're almost certainly going to be running very expensive corrosion resistant alloys. As you increase the wall thickness, your casing bill goes up quite considerably. So if we can keep the the casing string as light as possible, as low a wall thickness as possible, we keep our casing costs down. Okay? But what's the other knock-on effect of running heavier wall casing? It's the fact that we have to have a bigger rig. If we've got a heavier casing string, we need a bigger rig to hoist that heavy casing string. And that might be a considerable impact on the drilling costs of that project. For example, if we have a small rig and we're running a lightweight casing, that rig's perfectly capable of drilling the well that we want. But if we suddenly specify a heavier wall thickness in our 9 5/8 casing string, for example, that rig may no longer have the hoisting capacity to actually run that casing string. I would argue as well that you could look at using techniques from the extended reach drilling discipline. You could look at floating that casing in, even though it's a small casing string. There are other ways of doing it, but this wellhead system allows you to not have to think about any of that complexity, because we're doing what we've always done in oil and gas, and we're dealing with the expansion by pre-tensioning the casing string after it's been cemented. The other thing that is quite useful, when we do our life carbon footprint analysis of our geothermal well, we've got to include the casing steel as being used up and lost in the hull. With this system, because we're not cementing all the way back to surface. We can do a traditional oil field cut and pull operation on our casing string. So we can go into the well just above the cemented section, cut the casing and recover the rest of the steel to surface, at which point that's discounted from our carbon footprint. The other thing that we have is we can actively manage the thermal growth, and we can reduce the amount of wellhead fatigue that we get from the expansion and contraction of the casing string. So to basically show you a little bit of a graph, it's a slightly wiggly line, but we can put an AI system on that and it will tell us what's happening in the well. We have rising alarms, we have threshold alarms, we have falling alarms, we have rate of change alarms, and with a little bit of software development, we could very quickly have smart alarms that tell us when we've got an increase in pressure in the annulus just due to thermal effects, or whether it's due to a leak developing in the casing string. The other thing that we can do if we've got an open annulus is that we can actually physically sample the fluid that's in that annulus and sample it for corrosion products. Those corrosion products will be in the annulus fluid, and if we've got an open annulus, we can see it and we can treat it proactively before we actually have a problem. We've already mentioned the impacts of our annulus cement. We need large volumes, and as we heard yesterday from the cementing team, trying to circulate large volumes often results in losses. So we have to use exotic slurries, lightweight techniques like foaming the cement. All of those are additional complexity. And I'm a very simple person. I like simplicity in all aspects of my life. The other thing is, you know, with all deference to my colleagues in the cementing industry, when you ask for a high temperature slurry, the bill that comes with it is also high. And justifiably so, because these slurries are not ordinary Portland cement. They've put a lot of research and development into the development of high temperature slurries. And I believe that we are reasonably safe now with slurry design up to about 400 degrees centigrade. So how do we get the cement in there if we can't go conventionally? What we might have to do is reverse the cement down the annulus and up the string. And the problem with that is that the actual cement placement and the isolation from the mud is not as good. So we typically end up with a lot more contamination, a lot more void space creation. The other issue of cement is actually a relatively good conductor. Although we can go to a foaming cement, we can go to a cement with a lower thermal conductivity. Typically, cement is going to conduct the heat from our well much more efficiently than leaving a fluid in the annulus, or even better, a very simple external foam-based insulation sprayed on our casing. So what we typically have is we have a thermally productive zone down here. That's the desired temperature we want. So anytime our flow is lower in rock that's lower temperature than our desired temperature, that rock is thermally parasitic. It is stealing our money. All of this rock is stealing money off our project. So what we want is we want as low a possible thermal conductivity to the formation. And because we've got an open annulus, we can run a very simple low-cost foam insulation or sleeve on our casing string, and that will reduce the loss of temperature to surface. And when we start to look at what that represents in terms of value to the project, these are some calculations that our reservoir modeling guy did for this project. and you look at the improvement in thermal performance of this relatively low temperature well, and remember I can't remember what the inputs are. I think it's only 120 degrees, this well. So these numbers get bigger very quickly as the temperatures increase. So over here, we're looking at a performance increase, and this is over 30 years, by the way, of 238 kilowatt performance improvement just by having the ability to insulate the annulus. And this is a relatively small, conservative well design at low temperature. As we go to higher temperatures, as you have a bigger difference between the bottom hole temperature and the parasitic rock above it, the benefits are bigger and bigger. So imagine you having essentially, for some of your projects, I would imagine that the figures are going to be in the region of 1 or maybe even 2 megawatts better thermal performance at surface over the life of the well. That represents a very large amount of money as electricity to the grid. Your electricity to grid is not the same as your thermal performance. You've obviously got your conversion loss of the generation system that you choose. So is this all pie in the sky? Is this all a fantasy? No, we're actually under test right now. We have tested the metal-to-metal seals that we intend to use here, and even if you don't want the full geolock system, the metal-to-metal seal technology is now 400 degrees, so we can give you a wellhead that will function at 400 degrees C. We have already the technology to put the ratchet system in the wellhead, and the tooling is being developed so that once you have cemented, you put your wellhead on and the tooling will pre-tension your casing string. You don't have to maintain that tension in the casing string for the life of the well. We can come in and release in stages that tension. So if you're intending to go into a long period of maintenance shutdown for that well, what you would do is you would release the tension from the wellhead and allow that casing to contract without exceeding its tensile strength. What we need to do is we need to find a location that would like to use this technology, because like everything else, running it for 1 or 2 wells is not economically viable. If you have a project that has 10 or 12 wells, it would be good to start talking to OSI right now. The lead time on a standard wellhead at this moment in time is around about 9 to 12 months. Although last week I was told 18 months is now the lead time on wellheads, but that was just from one manufacturer. This being a new technology, you need to work with the company to define what your actual requirements are going to be, and then we have to start manufacturing. We have to start making sure that we have the skills on the island to actually install and maintain these wellhead systems. But if we want to develop EGS, if we want to develop reservoir-dependent hydrothermal, we need to improve our wellhead systems if we want to get the higher temperature, higher enthalpy wells in the ground. And that's all I have for you today. I can do a dance routine if you like, but I wouldn't recommend it. Have you got any questions? Yes, go ahead.
Kevin, thanks for that. Just curious, if you don't have cement return to surface,
yeah.
How long does it actually take you from a conventional wellhead system? Is there additional time that I need to put it on, or what about my integrity?
Yeah. So So in terms of the time impact, there's virtually no time impact because the tooling basically sits on top of the casing head, and we pull tension, and because it's new technology and they're going through their IP protection right now, the details of how it works, basically it's a ratchet mechanism on joints of casing, and those joints of casing are screwed together with their proprietary Merlin technology, Merlin connector technology. So you pull up on the casing and it ratchets through the wellhead, unlike a traditional wellhead where you have a fixed distance based on your space out that you calculated before you ran the casing. That you could counter, and you say, well, how's this different from a set of emergency slips? You don't want to set your casing string in a geothermal well on an emergency slip set, because okay, in oil and gas that might work because the number of thermal cycles and the tension and compression differences are smaller. In geothermal, you really need that ability to pull a lot of tension on the casing string, much more than we would traditionally in oil and gas. And we have tooling, hydraulic tooling, that sits on top of the wellhead. You tension the casing string, and that might mean that you can unscrew a joint and take that off, but the system allows you to do that. It's like I say, it's in test at the minute, and they're looking for partners who would like to run it in the field. These guys have been making wellheads for a long time. They know what they're talking about. They've been making tension leg ratchet tie-down systems for many years as well. If anybody's interested, my email address, I'll share my email address with you, and I can share you the paper that we wrote to sort of justify to their management team that they should develop this technology. And like I say, it came about just because I saw their tendon tensioner model on the windowsill. So hopefully it'll come to market. And by the way, I don't get a single cent from either Eden Geopower or OSI Renewables. I was paid to do some reservoir modeling, some thermal modeling for them, but I'm not paid to be enthusiastic about their product. The only reason I'm here is I genuinely believe that these technologies will be useful here in Taiwan. Okay, any more questions, guys? Yeah, go ahead. Yeah. I think the problem with the flexible coupling route is long-term integrity is the concern that I would have, but I don't have any direct field experience of flexible couplings. But it is something. It's something that quite often gets brought up when we say, well, this is a solution. Like anything else, there are other solutions. We just think this one might be the most elegant and the straightforward option. So, any other questions, guys? Okay.
Okay. No,
Thank you very much indeed.
Yeah. Thank you.